Good morning. I'm Jim Jones. I'm relatively new faculty member here. Our research, my research group's research, targets software maintenance. And typically the way that we sell it is targeting the task of debugging, because I don't need to convince you or funding agencies that bugs are bad. Software maintenance in general, it's a little more nuanced and I have to explain a little more. So, debugging. But we have this particular kind of flavor to the way that we do our research to target such debugging. Specifically, we utilize evidence to support comprehension of the complexities of our code. Because our code is huge, it evolves over time, its dynamic runtime behavior is complicated. Everything about software has inherent complexity. So comprehension is just generally a really hard problem. Now, there is a lot of evidence that we can use to help people understand their programs. Every day, we're creating more and more and more artifacts that are captured and recorded, such as the source code, bug reporting systems, revision control systems, knowledge, in our heads of authorship and areas of expertise, test suites, and so on. We utilize this kind of evidence to help support comprehension. And we do that with a variety of different techniques, such as program analysis, software visualization, textual analysis, and so on. Now, in a study of 80 industrial developers, Gilmore watched the way that people debugged their software and conducted a number of surveys and in different structured empirical methods. And one conclusion was that the success of the experts at debugging was not attributed to better debugging skills, but to better comprehension. So thus, we try to support comprehension. So what do we have today? We have interfaces that look something like this. And this is great, because this is way better than we had before we had symbolic interactive debuggers. We can go in and we can look at the state of each of these variables. We can put breakpoints. We can step through this program. But still, comprehension-wise, that's still pretty hard. One of the questions you might ask is, where should I look? Where should I put my breakpoint in this program? That's not necessarily an easy task. For some bugs, of course, you just know, and you're just going to go fix it. And that's not the type of thing that I'm trying to support. It's for the cases where it's not easy to say what you should do. But we have some evidence. Many of you have seen tools that support code coverage for the purposes of test adequacy. So you do white box code coverage, so you can see how much of your code has been tested by your test suite. This allows you to say, oh, actually, we haven't even tested that part of the code over there. We should have no confidence in its correctness. So let's add some test cases to the test suite. So we already capture this, or many of you already capture this. We can utilize this to help inform some of that comprehension. Imagine if we took that code coverage and we shrunk it down so we can see the entire program. We could look at different test cases and see that they execute different parts of the program. Every single time that the program executes correctly, we should have more confidence in every part that was executed. We should have no confidence in the parts that are not executed. But on the flip side, every time that the program is executed and the program behaves incorrectly, we should have skepticism or suspicion of the lines that were executed there. Now, if you can imagine, we can utilize all of this information together to support some kind of a correlation analysis. So if we are incorporating two test cases, we could say green lines are the lines that were executed only in the context of when the program behaved correctly. Red lines are the lines that were executed only when the program executed incorrectly, and yellow were in both cases, so we don't really know. if we continue to add test cases to our test suite, our correlation analysis gets better and better and better, and we can start to localize the parts of the code that were always, or almost always, executed in the context of failure, but not executed in the context of success. So this supports the problem of answering where is the bug. It doesn't tell you where the bug is, but it supports the comprehension of it. So it kind of directs your attention. You say, you know, you probably ought to look here, or there, or there. Success has been, you know, in the lab on our programs, we're getting the bug about 90%, or about 90% of the bugs within 10% of the code. Again, this doesn't solve the problem, but it supports the comprehension. Nevertheless, even with that information, you're still back in that debugger, and you're still scratching your head trying to figure out what is the bug. So yeah, I have some ideas about where it is, but I still need to figure out what is the bug. One thing I noticed in my dissertation studies was that we applied this to, I wrote a static analyzer for Java, and it had to handle exception handling properly. We had a lot of problems with try-catch finally, specifically with the finally handling of how that works in the bytecode. But when I would look at the results of this tool, I would see, if I looked at this source code, you zoom in and you see the source code here, you would see some code that deals with the functionality of finally. You'd see that string in there. In the comments and in the variable identifiers, the method identifiers. You look at another kind of orangish red area, and we'd see some terms that look like this. So we could start to see some patterns here, right? And that only happens because our brains are really good at seeing these kind of patterns when you look at each of these individual places in the program. So we started thinking, well, why can't we automate that process to help people understand what might be wrong with their program? And so we do some correlation analysis and some textual mining, information retrieval techniques to extract these words out of the source code, because our source code is full of evidence of what the semantics are and what the purpose of the different parts of the code are. And by doing that, we can produce a word cloud that looks something like this. Now this can happen automatically. We run our test suite, immediately upon we get some failures, boom, we have a result like this that pops up. Now, on a lot of our test cases that we've experimented with, we have like 50% of our test cases failing. So you can't just look at the test case and say, oh, I know what the problem is, specifically for, especially for system tests. So something like this, we can look at that and almost immediately know, okay, I don't know exactly what the problem is, but my comprehension has been aided by understanding the domain in which the bug is. So this supports the task of answering what is the bug. My PhD student, Nicholas DiGiuseppe, will be presenting on this topic at the poster session. So come talk to me and or him about this. Of course, now the next question is, who should be looking at this problem? And or the unpleasant flip side of this is, who's to blame? I'm not going to, one or the other. Really, the more important thing is who should be addressing the problem when we see it. We have bug reports. They get assigned to people, but it's using manual knowledge of who does what, the symptoms that you see on the exterior of the program, and sometimes you can do really well, but often we reassign the developer from bug report to developer, developer to developer, until it lands in the right hands. But we have some evidence that we think we can use to help automate the process and give more comprehension of who is actually the right person to fix bugs. Well, we have repository logs. We know who committed what changes when. And we can see we have a number of different commits, merges, we have authorship, we have some kind of log messages here about who did what. And using the correlation of where we think the bug might be, and using the history, we've created techniques that mine the history, map every line's history back to its origin, and then can advise on who is to blame, or on the flip side, who is the best person to fix this bug. Who knows that code best? So we're supporting the task of picking a developer by basically assigning suspicion to them. And so for this task, we're supporting the comprehension of problem of who should fix this bug. My PhD student, Francisco Cervant, will be presenting on this in the poster session, and you should talk to me and or him. All right, so now we know, well, we have some support for where the bug is, what the bug is, and who should be investigating. But now we have to say, okay, how did it get there? We need to understand what has happened, the cause, the state of the system as it is. In solving the authorship, the expertise problem, we realized that there's another problem embedded within that, and that is mining the history and doing a fine-grained history analysis of each chunk of code. We pulled that portion out and created a tool that
is unreadable.
It is unreadable, yeah. Which is why we have, let's see if this works. Zooming.
Ah, yes.
So what we have here is, and I'm not going to be able to go through a full demo here, but what we have is the ability to specify fine-grained queries of where we want to explore the history. When we look at log messages, we have a per file granularity, and or if we're doing, say, just like a SVN blame or something like that, we only have a pair of versions, so only one version back. Here we can support any number of versions all the way back to its origin, and fine-grained querying. So we can say, I want to see how this method changes with this method in a different file. Only those methods. I don't want to see every change that happens to those files elsewhere. And by doing this, we get images that look something like these. At the top here, we have a timeline that shows you, it's too small to read, but there's actual dates here. We can see where the commits are to those parts. These are two different files. So we can see that this method evolved, these two methods evolved roughly the same, but have some inconsistencies in the way that they were actually maintained. This might actually help us understand where the problem, or when the problem was actually introduced. We can see who introduced them and when, and we can actually see those fine-grained diffs. So this supports the problem of when the bug was introduced and partially why. This is again Francisco Cervant, who's going to present at the poster session. Okay, final piece. This is the end of my 15 minutes, isn't it? Okay.
4 minutes. You can use it however you wish.
One thing I noticed was that we had suspicious code that was in different parts of the program. Like I said, when we looked at them, we saw that they have similar functionality, but I wondered if they're actually related. Like, do they actually call each other? Is the bug somehow strung throughout them? What I wanted to do was basically free these lines of code from their position in their source code files. So we write those lines of code, those individual instructions, in a way in files and classes because it aids our comprehension while we're writing. But what I wanted to see was, if this calls that, or this exchanged some data with that part right there, I would like that task, that relationship, to be more comprehensible. So what we did was we do some program analysis techniques to understand all of the relationships, both statically and dynamically, while it's running in compile time, and basically let the statements go where they want to. Go hang out with your friends. Go hang out with the other instructions that you exchange data with or you work together with on problems. And we get a picture like this. This is the same program as that other program you just saw. So whereas we had red kind of in different places in the program, here we see that the red bits kind of come together. But we also see some other really kind of fascinating things like, what's this? What's that? Well, those are program features. Those are different parts that work together. Different program, we see a fault is clustering despite the fact that it's spread out. When we look at the way that the program is structured, we actually see that these different modules, in some cases, are split up. So you see that the util class is not cohesive. But we see other parts of the program that are cohesive. We can also see which parts of the program interact with different parts of the program. Now this is really, really early research, and I think this is not necessarily what I want to put in front of a developer and say, here, use that. But there's something here. Like this is really kind of interesting stuff. I also encourage you to go talk to Vijay Palapu. I guess I need to show this picture. Because we have another cool demo that I've run out of time, to actually show you, which is a live version of one of these graphs where different parts are lighting up as it's being executed. Kind of like when you see those Discovery Channel simulations of the brain, when you're thinking about something sad and then you think about something happy, different parts of the brain light up. This happens here, and it's kind of neat. But I didn't have time, so thank you.
Got time for about 2 minutes of questions.
Okay, good, great. Right.
So what I'd like to see is dynamic analysis as the system's running. In particular, what's the code taking place just before all that red error handling code occurs? So have you looked at that at all in terms of tracing back?
Yeah. So it really kind of depends on the bug. Different bugs are different ways, are correlated with failure differently. Sometimes that code is executed by all test cases, so the stuff that precedes it is executed by both passing and failing, so we have no highlighting of it. Okay, I think I know what you're saying. You're saying that the error handling code is the stuff that's going to be correlated with failure, and the stuff before it might be executed. It's true in some cases. We found that a minority of the cases that we looked at were that way. And actually, some of the work that we're doing with Vijay, one of my students, is trying to help do that kind of backward analysis to lead you back to where the error state started. But in many cases, the code that's responsible is actually highlighted by, it doesn't have to be all 100%, but as long as it's more often than passing, we get highlighted that.
Okay, thank you, Jim.